Our guest today is Rogerio Panizzutti, and I am just going to call one other person. And Dr. Panizzutti has degrees from the Federal University of Rio de Janeiro, and he is a psychiatrist and I guess a neuroscientist.
Hi, Jamie.
And so he's going to talk to us today about something that we're all very interested in, and that is cognitive training. The big question that you've always asked me is, what can we do? What can we do for our loved ones? What can we do for ourselves? So, Rogerio, welcome. Thank you so much for being with us.
Thanks, Jamie. Sorry about we had some trouble here and I cannot show my face, but I think that's better to show my slides than my face now. And
thank you.
Welcome everybody. It's a great pleasure, Jamie, to be talking to this audience. I think that we have to share and discuss about the new advances in terms of how we can promote brain health using digital tools such as the cognitive training that we're going to talk today. And as Jamie introduced myself, I'm an associate professor in Rio de Janeiro in the Federal University, and I'm Atlantic Fellow of the Global Brain Health Institute. In the Federal University of Rio de Janeiro, I am the director of the Lab NACE, which is a laboratory dedicated to studies related to digital cognitive training. Today I'm going to make a little roadmap. I'm going to show you a little roadmap about our talk today. I'm going to talk about how we can engage neuroplasticity, this amazing capacity of the brain to change itself through the life. And next, I'm going to talk about neuroplasticity-based digital cognitive training. So how we can use the principles of neuroplasticity to induce improvements in the brain functioning using digital tools. And in the last part of my talk, I'm going to share with you some new information related to how we can prevent dementia using digital cognitive training. And the first question I'd like to ask, and that's a very important question, is that in which degree we can change the adult brain. I mean, this was a question that's been around the neuroscience for a while now, and it's important to understand that as we learn about neuroplasticity, looking at the brain of subjects in the childhood or even before. So we used to not know so well how those principles of neuroplasticity would be applied to the brain as we get into the adulthood, and even how neuroplasticity works in the brain as we age. So to face this problem, my supervisor is an emeritus professor of the University of California, San Francisco. He was my supervisor while I was a fellow at the University of California, San Francisco. His name is Michael Merzenich. And in the 80s, he tried to challenge the idea that the neuroplasticity was something that we could do very well in our childhood, during our developing time, but after we could not change our brains so well. And just to have an idea, when I was studying medicine in the beginning of the 90s, and when I got into the medical school here in Brazil, the concept that we learned at that time was the brain would not change after the end of the adulthood or the teenagers, after the end of the childhood and the teenager time. So we learned that after that time would just go down in terms of our brain capacities, and that's been shown from several research institutions, several research around the world. That's not the truth, and Michael Merzenich was one of the first to show that. So In the next few slides, I'm going to show some few experiments that were used to base the idea that we can really change our brains during our life, and that's an amazing characteristic of our brain that make us so adaptable to the environment. And just I'm gonna show you some neuroscience principles. So, and I'm trying to make this in an easy way. And after we can discuss about that. But we know that in our brain we can probably you already saw this image that shows that in our brain the different parts of the brain are represented in different parts of your body are represented in different parts of our brain. And that makes one map in the brain that we call somatotopic map. So when you talk about our sense of touch, it's represented in different regions in our brain. But the question is that one important feature of that's the proportion of those regions are not related to their actual size. And if you put this information together, we draw what we call a sensorial homunculus. Probably that's a very common image in neuroscience that shows that we have very big representation of our hands, from face, but not so much in our arms or legs. And the question is whether this could be changed with experience or somehow during adulthood. Because that's when you make your sensory homunculus, this is organized since the beginning of our experience. So when you are a kid and we're a baby and start to connect with the world start to touch us, to talk to us, we can start to feel the world around us. Those maps are organized in the brain based on that information. So, and the question that is whether we can change this during adulthood, and it's so as I showed, we can draw you can find in the brain the areas that represent different parts of our body. And this is we have an example here with the fingers of the hand, showing that different areas of the brain are represented in different fingers. In this case, are represented in different areas of the brain. And the question that is can the experience change this cortical, what we call cortical maps in adults? And that's one question that's been studied in different forms, and those studies have been carried out in the University of California a while ago, now like 2 decades ago, and showed that if we have this representation, that time people are studying in monkeys, we can see that the representation of their fingers can find that representation in the brain. And first studies were done in 86 that showed that in case of an amputation, if you miss one of the fingers, there is a change in our brains. It means that the representation, the area of the brain that is responding to those fingers, it's expanded to cover the area of the brain of the finger that was missing. So that was the first evidence, and that happens in the adults. And that was the first evidence that the brain can change in the adulthood. That was back in 1986. But of course, that's not what we're interested in. We're interested in how we can drive this kind of plasticity in a good sense. And to carry on that, in the beginning of the 90s, it was published the first study showing that if you take monkeys and put them to do an intensive rewarding training, it means that in this case the monkeys had to touch a rotating disc, and every time the monkey would be able to touch with the second and third fingers the black parts of the rotating disc, this monkey would get a banana pellet, so a reward for this behavior. So the animals would work on that and be trained on that, and it's very clear that they get engaged on that. They get excited about the training because they get the reward out of that, and that uh, when you look at the brain of those animals that were trained, we can see that what's happening now, that the area that was representing the G2, G3, it's expanded after the training. So that was the first evidence that we can really change our brains, and this is in a sustainable way, because if you study this 6 months after the training, this area is still expanded, showing that we really can change our brain depending on how we train this. And that was the first evidence that was found in monkeys, but just after that was published 2 papers, and this one of the papers I brought here, showing that that's not true only for monkeys, but also in humans. So when researchers studied string players, musicians, they could find that the size of the representation of the fingers in the cerebral cortex was larger in string players when compared to controls. That means that these subjects, they've been involved in an activity, in a training. They've been learning about how to play music, and if they practice more, the size of their representation, the brain is larger, showing that it's really, we are really able to change our brains during our life. And that's a very, for me, that's very exciting find, because show that we can always change the course of things if we move this. And we can see this very clear when you look at the physical body, but this evidence show that is also true for the brain. And so we can conclude that the adult brain is adaptable, and that's something that we can change in the brain, and what you call neuroplasticity, this capacity, this amazing capacity of the brain to adapt itself to the environment, and learn with that and change it profoundly. But what allowed the brain to change, or what do we need to engage neuroplasticity? So in the next 2 slides, I'm going to show just 2 experiments, and that show some of the principles that are related to neuroplasticity. And we know that in the auditory cortex, so that's the area of the brain that receives the information, the auditory information first in the cerebral cortex. So that's where we at first we listen. And we know that when we develop during the childhood, when we start to be exposed to the sensory information, as I said before, our brain can change dramatically. And so that allows us to adapt ourselves to an environment where we're going to be growing. And of course, that's different if you compare a kid that's growing in Japan, that's exposed to Japanese language. It's going to be, he's going to develop a cortex that's going to be very adapted to listen the Japanese language. That would be pretty different if you compare, for instance, with a kid that is raised and born here in Rio de Janeiro, that's been exposed to the Brazilian Portuguese language, and so on. So, and this process, it's important to understand that this process, it happens in a passive way. I would say kids don't make a choice if they want to learn and adapt their brains to this or that. So they just absorb. It works like a sponge, I would say. That's a term I like to share with my medical students here. It's that the brain, it's capable of changing just as a passive exposure, and that can be shown here in a study that was published by a colleague from at the CSF, and now he's at McGill University, and showing that that's the map. We can map the brain, and that's in rodents. That's different regions of the auditory cortex are responsible to listen for different frequencies of sound. So neurons more in this area respond preferentially to sounds in lower frequency. Here more go to higher frequency. And if you take this up and expose this just exposure while they are developing to a specific sound, in this case was used a specific sound in the 7 kilohertz, it showed that just the passive exposure increase the size of or the number of neurons that respond to that specific sound. So just passive exposure. And if you do the same experiment in adults, that doesn't change. So the adult brain works different, and that's the point I'd like to highlight here. So passive exposure to sounds does not change the adult auditory cortex. So what do we need to change our brain while we're adults? When we know that it's not the same process, it's not so easy, I would say, to induce neuroplasticity in the brain of adults, and because probably what the concept that we have now, that actually the brain organizes itself during this period of development, and then to change now they need a little bit more. They're not going to change just to be exposed passively to a stimuli. And to understand the factors involved in that, we can work on, and that was a study that was done in the lab showing that they studied one area that we are it's very important when we focus our attention on something that's called nucleus passalis. We know that when we're paying attention to something, this area will be activated. And what they did here, that they artificially activate this area and pair this activation with a sound in the frequency of 8 kilohertz. So the paradigm here is that it's the exposure, every time you are exposed to the sound, you will receive a stimulation in the nucleus basalis. This was made in rodents. This was done several times. So during few weeks, the animal has been exposed to this stimulation of the focus and attention area, and just passive exposure to a sound. That was made in adults. So just the passive exposure to the sounds would not change this brain, as I said before. But after we do this paired with the stimulation of the focus and attention area of the brain, the results are very dramatic. I'm going to just show you can see here that the area that was stimulated, this 8 kilohertz, now expanded a lot, and it covers a much larger area than an animal that was not exposed paired to the focus and attention area. So it means that neuroplasticity depends on focus and attention, and that was published in one of the major journals in science. It's called Science in 1998. And another point that was studied was that what about reward? They showed that the training was done, it was based on reward, that training that changed the brain in the monkeys. And what's the role of the reward? How can you engage reward and get this driving neuroplasticity? So here the experiment was a little bit more complicated. What was done, that was played a sound in 4 kilohertz, and this sound was preceding the stimulation of the ventral tegmental area. Ventral tegmental area is an area of the brain that's activated when you get rewarded. It's also activated when you get when you eat chocolate, for instance. So everything that gets us excited, and usually it engages the ventral tegmental area. Chocolate, good things like chocolate engage this. Not so good things like gambling engage this area, or even some drugs of abuse are involved in this. But it's very important, because if you don't have something that makes us engaged, makes us excited, how can we learn if that? It definitely wouldn't work. And this experiment was very interesting, because what was done, that was show that we simulate the 4 kilohertz sound. That was preceding a stimulation of the ventral tegmental area, and next the trailing sound was 9 kilohertz that was played after the simulation. So the question is that which one would drive plasticity? The first sound. So we play the first sound, we stimulate the area of the reward area, and then we play the second sound. And the results show that the reward should be just after the stimulus that's been presented. In this case, the 4 kilohertz. So the 4 kilohertz will increase a lot in the brain, because this was preceding the ventral tegmental area. So if you want to get the reward, it's very important that the rewards should be offered after the what we want to learn. We do this with dogs. I mean, if you go to the park, want to train your dogs, you're going to give the dogs, we're going to you're going to make the dog to do something, and every time that the dog does a good job, you give him a reward. That's very common, and that's what happens in the brain. So if you do the 4 kilohertz before the ventral tegmental area, it increases the area of representation of this. But if you show the 9 kilohertz just after the reward, doesn't change the brain. So it means that the reward should be really just after the stimulus that we are trying to use to induce neuroplasticity. And that was that highlighted the importance of reward for neuroplasticity. So I try to convince you now with this some of these studies showing that neuroplasticity depends, and that's very clear, and that attention, focus, and rewards is very important. And if you think about somebody that's trying to learn how to play guitar, for sure, the person has to pay attention what they are doing. They have been training, being focused on while they are training. They get reward when they get they play a music to their friends say, oh, that's nice, and so on. But another point is that nobody learns to play guitar, trying just once. So we do need something else that's thousands of repetitions. Nobody learns without training and without training hard. So repetition, reward, attention, focus are some of the pillars of neuroplasticity that applies for the neuroplasticity in the adult and older brain. And we know that we can. The concept now is that we can use those elements in video game-like exercise, and that's what we call neuroplasticity-based digital cognitive training. We know that video games are very efficient on calling attention, make people very focused on that. The people really get reward and they reach some of the levels of the game. They don't play this just once, they play this a lot of times. But of course, if you want to use this as a tool to improve, to engage people and to be able to promote health in different ages and different populations, we have to adapt ourselves. So a game that could be interesting for a kid or somebody that likes cars would be not so interesting for an old lady with different interests. So we have a lot to learn how to make exercise that are more engaging and so on. And that's, of course, that's a big opportunity for us researchers to play and work on that. And we work together with this partner, Mike Mercenich, and we participate in the development of a platform, several of exercise that use those principles. And this is an online platform. You can go there and train your brain as you want. There are several other platforms in the market that are available. So it's very important to understand what the effects that those exercises have in the brain. And this kind of platforms, you can understand how much you are progressing in the training. So that was my training 1 year ago when I was 41, showing that I was advancing and I was getting stars and so on. So that's an important part that you can track our progress. And what the idea is here is that we are doing is that we do exercise our brains to reinforce tasks that are relate pathways that are engaged in the exercise. And after this, what to expect that we have changes in the brain that are stabilized after weeks of training. And one point that's very particular of this kind of trainings, that they are not working only in our memory. It's very common here in Brazil and in US. I've heard that there is some what you call memory workshops that people train their memories and so on. That they have effect, but those effects probably are not so more limited, because those exercises work only on the memory. And with a digital platform, what we can do, and that's very important, if you want to train your brain and look for a digital platform to train your brain, it's very important that the training doesn't cover only your memory. It's important that covers your capacity to inhibit your behaviors, to work on your attention, and very important to work in our perceptions, auditory and visual perception. Because we know that as we get older, our capacity to perceive the world, it starts to decrease. So it's very important that you have you have an exercise, that you have a very engaging training, but that covers those different aspects in the functioning of your brains. And I'm just going to show you some few exercises to have an example of how those exercises works. Hope that would work in your computers with the sound. And can you hear the sound? So here what we have to do is we have to sorry, it's written in Portuguese because I adapt this platform to Brazil, but those are available and original they are in English. And what we do here, see here that we have to, the exercise here, we have to follow one of the balls, the circles in the middle of the others. And as you get better, you see that now I have to follow two circles in the middle of the others. The circles start to spread as you get better, they move faster. So the exercise is adjusting the level of difficulty all the time, trial by trial, to always to reach my 80% performance. It means that the exercise can change the difficulty, the level of difficulty all the time to make us getting better. So now I have to follow 3 of the circles, and we see clear that as I make the right choice, I got a reward, like some fireworks as a way to get reward. And now it's going to be a little bit harder because this exercise I'm more advanced when I played to record this video, and the task here that those eagles would you blink, and one of these will be different than the others. As you get better, they will be faster and faster, be harder and harder. And you're gonna see that for a while I was getting better, and then I clearly reach a level where I was struggling. So that's the level when I work on. So the exercise, they can start very easy, but they can get very hard if you're doing well. And that's important, because if the exercise is too easy, would not drive plasticity. If the exercise is too hard, we would not get engaged on that. And that's something we learned from the basic neuroscience. And just to show now, it's kind of okay. You have to show where the quadrant that the eagle show up. And I'm doing well now, but yeah, I'm gonna see that I'm gonna reach a level where I'm gonna have some difficulties on that. You see that it's so the exercise is always adjusting. That's something. That's why we call digital cognitive training. That's the next generation about cognitive training, because with computers, with tablets, and so on, we can definitely organize the exercise in a way to challenge our brains in a continuous manner. You see, that's very hard, and even now, and it's hard to respond. But of course, you train better, get better, and so on. So you see that I didn't reach the level that I was supposed to reach on this exercise. What we've been doing here in Brazil, just share a few quickly one video showing how we've been applying this. This is I'm a professor in the Federal University of Rio, but that's in the Catholic University in Rio. Those are psychologists that work with me, and those are subjects that have been studying. They are practicing their brain with those kind of exercise, and we are studying this in a research context to learn how we can drive this plasticity in a better way. So we evaluate those subjects before and after training. Those trainings can be done at home, but they also can be done in a setting like this. And what we're doing here, we're trying to build what we call our cognitive reserve. So we know that while you get older, that's information that comes from the World Report on Aging and Health, from the World Health Organization. And it's kind of late for the World Health Organization to get engaged on that. That first report was coming out in 2015. I was there 2 years ago, 2016. I had the opportunity to discuss with the people that have been working on this report. And the idea is that while you get older, of course, you start to lose some of capacities, and this decline in the capacity can pass a border where you have significant loss in your functionality. And what you can do on that is that the concept the framework is that we should push this to the top. We should try to push our capacities since the beginning, kind of building what you call a cognitive reserve. Would be like my savings that I do over my life, and the possibility that I really cross the border of significant loss of capacity is postponed, or even we don't reach that. So as much as we push this to the top, is going to take longer for us to have a significant loss of capacity. So that's the idea, and it seems that things are changing somehow now in the society, because this was one study published in the New England Journal of Medicine, one of the most important journals in medicine, showing that when they look at the incidence of dementia of 3 decades in the U.S. in this Framingham Heart Study cohort, what they found that was pretty amazing was the fact that actually there was a large decrease in the incidence of dementia in this population, and this decrease was around 44%. It's very large. And the important thing is here that you have to highlight that this happened only in people with high education. So it highlights the importance of education. So people that are high educated, it's getting less dementia in the last decades in US. And that was associated with reduction in cardiovascular risk. We know that everything we do that's good for our heart is going to be good for our brain. So it's very important that you keep on that. And but still, there was something else that's been associated to this, and probably is related to education, probably is related to how we engage our brain in health activities, in activities that are very engaging. And that's something that was confirmed in a second study that showed a very similar result that was published in JAMA, showing that the prevalence of dementia is declining in populations with more educated population. And I'm going to show you the last exercise now. It's that's a very important exercise, because that's the exercise that's been shown to be able, at least in one study, in a large study that was showed that this exercise could help prevent dementia. And this is a very simple exercise. We're gonna the same principle as the eagle exercise, but now we're gonna have one car here in the middle of the screen. You have to identify which one of the cars is gonna be show, and also have to, at the same time, you have to identify where this Route 66 plate was presented. And the exercise is passed by a training part, and then the first is just identify the car in the middle. And now we go. You see that you have to find the car and also the plate where the plate was shown. And the exercise does the same principle as the other. So you see that it was very fast. I was not able to find it. And now it's lower, and now I can find. And it's always trying to make the things harder and or easier, depending on the level we get. What's important about this exercise? This exercise was designed actually to work on what we call a useful field of view. We know that our capacity to find details and to respond fast to information in our visual field It's better in this what we call useful field of view. This area that we have more information coming into the brain, more we are more aware about what's going on than in the periphery of your visual field. But what happens while you get older is that this user field of view gets smaller, as you can see here. And this, of course, affects, in this case, in this example, can affect our capacity to drive with safety. And that's very important, of course. And so this exercise that I just showed you is an exercise that was designed to improve the area of field of view while you are training. And it's been shown that several studies show that people that have been doing this exercise are capable to keep driving better and safer while they get older. And so that could affect their independence and their quality of life. And last year was published the important study in the Alzheimer and Dementia journal, showing that this exercise that I just showed you, it's capable to lower the risk of dementia when we look at 10 years after. And that's called the ACTIVE study. That was a study that engaged almost 3,000 older adults in the US. And those subjects were randomly assigned to 4 different groups. One was doing just memory training, just like pen and paper training. Group that people are doing tasks and so on using just papers and pen and so on. The same for reasoning training. So that's just training about reasoning and so on. And one of the groups, sorry, it's missing one letter here, but the speed of processing training, this exercise in the computer was done by one group, and the fourth group was just a control group that was not doing anything. When I looked 10 years after the training, so that this study was being run in the beginning of the 2000, and when I looked 10 years later, they found that just in the group that did the speed of processing training, the digital training, in this group, there was almost 30% reduction in the risk of dementia. So those subjects that are being trained in the computer, that was around 18 hours of training. 10 years later, they had less dementia than the group that was doing reasoning training or memory training, showing that it's important to change how our brain are working, and that can lead to some prevention in the future. And that's something very unique, because that was the first study at all to show that in an intervention that can lower risk of dementia. We know that people that let's say people that have more cognitive engaging activities, such as university professors, as myself, they're kind of protected against dementia. So the studies show that we have a lower incidence of dementia than the general population, but that can mean that we are more engaged on cognitive and challenging activities, and that is preventing. But another very, very possible explanation is that the fact that we are professors in the university, it means that we are kind of selected since the beginning, because we have more cognitive reserve that less dementia. So to answer this kind of question, we have to do really studies like this ACTIVE study, where do randomly assign people to different interventions and see what's going on. So this was very exciting to everybody to see that how much you can change your brain and how much you can profit on that. So just to summarize what we discussed here, and I'm going to open for questions, and is that we know that the adult and the older brain has an intrinsic capacity to change itself, what we call neuroplasticity. And digital cognitive training may improve brain functioning and contribute to dementia prevention, as I showed you. And one very exciting thing for myself as a researcher is that we don't know the limits of neuroplasticity. And so it means that we have a lot to do and a lot to learn, and many things we can develop and in order to promote brain health. And we feel that we are now in this stage related to cognitive training. We know that it works, but probably don't know the best way, and we want to work to have this, like in the physical exercise we do now, that we can have very specific exercise to each part of our brain, and that's how we want to approach this. Thank you very much.
Thank you. Okay, Rogerio, that was awesome. I'm gonna be the first to ask a question, because people with posterior cortical atrophy have visual and spatial deficits. Are there things that we can do to strengthen the occipital lobe and the spatial parts of the brain?
Yeah, Jim, I haven't put anything specific because there's no study with those exercises in this specific condition. But what we know, and I know from what I say is like is, I would say, more anecdotal information, is that we as much as we can engage ourselves in tasks like those exercises, let's say visual exercise, those exercises are very visual. We can expect that region, we can improve the function of that area. Of course, if you have a process that's it degenerates in a point that you cannot engage that area, that probably won't work. But I think that we definitely should exercise, and that's the exercise, and the advantage of the digital exercise, that they can very easily adapt themselves to each person's capacity.
Wonderful, thank you. I'm going to open it up for questions. Please just raise your hand and I'll unmute you if you have a question. Yes, Dave.
Just to follow up on what you were saying, most of the things he showed, you would need the visual, and I know Shirley would never be able to do any of those. So something's going to have to be developed where either the things are very much larger, or it's more by sound or something, because anything that he showed, she wouldn't be able to do, you know. And I don't know if he has anything other to suggest as far as exercises goes that wouldn't require the fast visual that you needed in the games he was showing.
Yeah, the point here, as I said, we are still struggling how to adapt each exercise. That's why I showed that when I present the idea of the digital cognitive training, I just, every time I show the idea, I show also the challenge. And the challenge is exactly what you said. The challenge is how to get a exercise that everybody can do. And of course, we wouldn't find exercise that everybody can do, but probably what we can do is try to adapt and try to see how find exercise that people can do with their capacity at that time. And for instance, there is one alternative that we can definitely think about is to engage not the visual domain, but the auditory domain. So if the person has more preserved, like you said, the auditory functioning, probably can get engaged on auditory exercise, and that's true. Those exercises are very they are hard to be seen if a person has more difficult. Of course, there is adaptability on that. We can increase the sizes and so on, but probably it get better with engaging in auditory exercise. I show you just the visual exercise now, but there are many exercises that are engaging the auditory cortex. And if you think about the way that the exercise could engage and promote the speed of processing of the brain, that could work not only with the visual, but also with the auditory. So I feel that, as I said, we don't know a lot of things, but we do know that the brain can get engaged, but it's really a challenge to get the brain engaged on those processes in different conditions.
Wonderful. I'm going to, somebody up on the chat asks, how would you explain an extreme visual and spatial loss, but the person can still play ping pong and run. Walking is difficult.
Sorry, Jamie, can you repeat that, please?
Yes.
Or
basically, they have an extreme visual and spatial loss, but they can still play ping pong and run, and walking is problematic.
Walking.
yeah. Sorry, I mean, I'd love to have a specific answer for that, but I really don't know the answer. I would guess that when we talk about activities that can engage our brain, and as I said about the dopamine and so on, I mean, when we get those activities that makes us that we can call rewarding activities like playing ping pong or so on, those could engage our brain in a way that would facilitate the process. So we know that the motivation it's a very important point in our brain, how to get on those things. But so one point possibility to be related to engaging and things that we can practice, and of course ping pong is a training to our brains.
I also want to mention something, that a lot of the problems that for people with posterior cortical atrophy in getting into trials for, say, Alzheimer's disease, which is a different area of the brain. The problem is that a lot of the tests that are given, the neuropsychological tests, are visual, right? And so a lot of people can't pass these tests, not because there's something wrong with their brains in terms of the memory and the attention, but because of the visual. And a lot of scientists, in fact, our guest next week can address this. Our lecturer on June 7th is a scientist from the University of Indiana who is just beginning a large multi-center study on early Alzheimer's disease. And so she will address this, because PCA patients, they're creating biomarkers so that they could figure out like what's the best way to test people with PCA, because they don't have the same kind of Alzheimer's, traditional problems. These are kind of unique problems. Anybody else have a question? I see. I'm going to just, everybody just be quiet, but I'm going to just unmute people, because there are some people who are on the phone and they might have a question. So I'm just going to unmute everybody, but just be respectful of the fact that this is being recorded. And if anybody has a question, everybody is unmuted, and we'll take any questions now. And if there are no questions, then that's fine also.
Can I a question really quick here?
Sure.
I had a little bit of trouble understanding what we were talking about with dementia and the correlation between higher education and cases of dementia. Were we saying that dementia is being seen more frequently in people with higher educations, or the other way around?
The other way. This goes back a long way. About 30 years ago, scientists began seeing a correlation between higher education and a lower risk of dementia. And no one really understood the correlation. And now they're beginning to understand that it's this concept that Rogerio was telling us about, brain reserve. The more you build up your brain, if you remember those studies he showed you from the monkey, where they're training on something and their brains are actually growing.
I wasn't able to view it because I'm just on my phone here, but I am going to go ahead and watch this once you've got it recorded and put up.
Thank you.
Other question I wanted to ask was mentioned that rewarding right after the learning, that seemed to stimulate growth better. Is that correct?
Yes, perfect. Yeah, definitely. We do not have to temporal association between the stimuli and the rewarding. And sorry if I was not so clear about the question of dementia and higher education, but yeah, what we've been seeing that studies specifically, as James said, that's something that's been shown in several other studies, but in those studies specifically, was that this decrease in the prevalence and the incidence of dementia that's happening in the last few decades in the US are happening on people that have higher education. So it means that probably these people, as they have more cognitive reserve, more brain reserve, they're being able to engage in more activities, get more out of their brains, and that's protect them for dementia. So it's that's highlight the importance of education and
right.
And,
No, that makes sense.
Rogerio, the Brain HQ site is brainhq.com, and people could probably go up there and log on. I've been doing that kind of stuff. I haven't been actively doing, but I joined those sites a while ago, and they're very interesting. And there may be tasks on there that you could work on, every day that you could do that are not just.
Well, I was wondering a question. Are there big TV games for something like this? Because we've got a tablet and phone versions of them, but they're just way too small for my father to see. Yet, if I could put him up on a big screen TV and maybe give him an old style joystick for like a old computer game, he might be able to do that.
Well, if you have a TV with a smart, that you could take your computer or your pad and put that onto your screen, a big TV screen, and have him do it that way. Rogerio, you have any idea?
Yeah, definitely. I agree. We have to adapt the screen to our capacities. Actually, we think that for those exercises, the cell phone screen wouldn't work, because we are talking about kind of field of view, and so the tablet, I would say a 10. A larger tablet will be okay, but if you get bigger, if you need more, there's no reason to not use a big screen with a computer and the controls that you can use. So those exercises are available in the web, so you can use this in a computer or in a tablet, or so it's very adaptable in terms of platforms, and in the Brain HQ there are more than 20 exercises. So I showed some few examples, but definitely there are several options. Important to find the one that yourself.
We don't have a computer monitor large enough for my father to see, but could those things maybe be accessed on a smart TV through YouTube or okay? Okay,
yes.
super. And the other thing,
why don't you just send me your contacts through Facebook, and I will call you and help you do that for your dad. How's that?
Okay, that'd be great. And I just also wanted to point out, I don't know if a lot of PCA patients have this, but my father's unable to use the buttons of a keyboard anymore, but I do feel like an old-fashioned joystick might work a lot better for him. So I don't know if there's any way to, one of the things my sister-in-law does is develops video games to help autistic children learn, and she's big on this neuroplasticity thing. So anyway, I'll email you later and we can talk about it.
Wonderful.
Thank you so much.
Thanks, Meredith. Anybody else have any questions, comments to share? If not, we'll say thank you, Rogerio, and thank you all.
Yeah, thank you so much.
Thank you, everybody. This will be recorded and it'll be up in a few hours. Rogerio, thank you so much.
Thank you, Jamie, for the invitation. Thank you, everybody, for the audience. It was a great pleasure to share some of this information. That I'm available. Sorry, I didn't put my email here, but through Jamie, feel free to share my email with people that are in need of information.
Thank you. And I have one request, Rogerio. Can you send me a list of sites that I can share with my peeps
Sure.
Wonderful. Thank you,
Sure.
guys. See you.
And that would be really helpful.
Thank you, everybody.
Thank
Thank you.
Bye-bye.
Okay, are we done?
We are done.
Okay.